Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science and the paper is data structures. In this particular module, we are again going to continue talking about trees, and in this we are talking about a different type of tree called splay tree. It is a self-adapting trees. We have looked at lot of balancing trees. We started with normal general trees, then we went into specific type of trees called binary trees, then we went to a more specialization of binary trees which was the binary search trees, then we went into specialization of binary search trees which we call as balanced binary search trees. In the last 3 or 4 modules we had looked at these type of balanced binary search trees, which was basically we looked at 2 types, basically AVL trees and red black trees. Now, in this particular module we are going to look at in those type of balancing we did a height balancing. Here also we are doing height balancing, but in addition we are going to do a little bit of self adaptation which we will continue to see as we look at in detail about this particular tree, the splay tree. So, these are the people responsible for the creation of this module. And so, let us go into details about the learning objectives of this module. The learning objectives of this module are as given, that is, one is to understand the idea behind splay trees, because this is slightly different idea from normally balanced trees, balanced binary search trees. Then we are going to look at different cases of splay trees, then we are going to describe the operation of splay trees and then outline some of the advantages of splay trees and also by the way the disadvantages of splay trees if they are. And then here we are going to the key terms we are going to talk about are obviously splay trees, and then zig and zag cases we will see what this means, and then splitting. So, these are some of the keywords associated with this module. Now, let us go and start with the basic idea of a splay tree. So, blind rebalancing. So, this is blind rebalancing, that is no height information is kept. Remember, in both AVL and red black we had in AVL we had the height information, in red black we had the number of black nodes and black height and all that, we had black height we had BH. Here we are doing blind rebalancing, we will see what that means, but no height information is kept and worst case time will be of the order of n as in a normal thing. Worst case amortized time, that is, you remember what is amortized, we have already seen this. This is the average over a number of n operations is of the order of log n. So, we are not guaranteeing that most every time you do an operation it will be of the order of log n, which we did in balanced binary search trees, but we are saying that on an average it will be of the order of log n the time. And insert find always rotates node to the root. So, this is the crux of the algorithm. The splay tree concept, that is insert and find operations on a splay tree will always rotate the node that you try to insert or the node that you try to find to the root. We will see, that is why it is called self adaptation, we will understand this as we go along. And then it is a good locality, that is this is the basic what do you say philosophy of splay trees, that is the most commonly accessed keys move higher in the tree, become easier and easier to find. So, the more commonly you use a key, that key moves higher up the tree, and when you move higher up the tree obviously it is easier to find. So, this is the philosophy behind splay trees. This is the idea of locality, they call this an idea of locality, because the more commonly accessed ones go up the tree, okay, keys. So, let us go with the idea. So, here you have a small tree and the keys are forced to make a so for example, if you want to find a node here, you are forced to make a really deep access, okay, let us assume. Now, like example, you want to find this particular k, you have to make a deep access. Since you have down there anyway, fix up a lot of deep nodes, take a lot of deep nodes and try to fix it up means move it higher. So, move n to the root by a series of zigzag and zigzag rotations followed by a final single rotation which we call as zig if necessary. So, this is the basis. So, what you have done? You have gone to a deep node, since you are there anyway, okay, you have a lot of deep nodes there. So, try to move those nodes up the tree, this is what we are trying to do. So, if you want to move up the tree means to the root. So, suppose you want to move n to the root, what do? You do it by a series of operations which we call as zigzag operations or zigzag operations. We will define what the zig and zag are. These are new terms that we have not seen up to now, and it is followed by a final single rotation. Rotation is the same, some of these rotations are similar to what we saw in AVL trees, but slightly different, we will go to that, and the terminology used is different. So, here single rotation we call it as zig operation if necessary. So, this is the basic idea of a splay tree. Okay. Now, with that idea, remember what the idea was? The idea was that, remember the philosophy is most important, you must keep that in mind. If there is a node that you have accessed, now the idea behind is this node is likely to be accessed more frequently next, and so try to move this node higher up the tree. That is the principle of locality. That is, if you have accessed something now, you are likely to access nodes near that or that node next in the coming future immediately. So, that is the philosophy that this splay tree is trying to propagate, okay, or make it easier, make it faster. So, splay trees are binary search trees. So, just like AVL trees was binary search tree, red black tree was essentially a binary search tree, splay tree is also a binary search tree, okay, that is there. So, remember binary tree, you know the property, binary search tree, left key is less than the root and the right tree nodes are keys are greater than the node lexicographically. But the idea here is they are not perfectly balanced all the time. Even in AVL we did an approximate balancing, here they are again we are saying that it is not perfectly balanced all the time. Okay. Allow search and when you are doing a search and insertion operation, during search and insertion operations, we try to balance a tree such that future operations may run faster. So, that is the essence, again and again we are talking about that philosophy, and that is the core idea behind splay trees. So, what you do when you do a search or an insertion operation, you are trying to balance a tree such that the next time that you do you try to find those keys, they may run faster. So, that is the idea. So, it is based on the heuristic that if x is accessed once, it is likely to be accessed again, okay. That is the principle of locality. And after node x is accessed, we perform splaying operations to bring x up the root to the root of the tree. So, that is what we do. So, after you have accessed the node, at the first time you access the node x, wherever it is there, it will be there. But the idea is after you access the node x, either through insertion or through searching, once you do that accessing, then you perform a splaying operation such that you take this x up to the root. So, what will happen the next time you access x, it will be much faster. Okay. So, that is a splay tree, and do this in a way that leaves the tree more or less balanced as a whole. So, not only do you ensure that x moves up the root, you also ensure that when you are doing this splaying operation, you ensure that the tree is more or less balanced on the whole, not only for this particular node. So, let us take an example. Here you have the root and this is the initial tree, let us assume. Now, let us assume that we want to splay with 12, that is we are searching for 12 or accessing 12 or something like that, and we splay with 12 and make the tree balanced, and subsequent access for 12 will take of the order of 1 time, not even log n 1 time. So, what we will do is active or recently accessed nodes will move toward the root and inactive roots nodes will move down the tree further from the root. So, what we do here? We do a rotation. This is a normal rotation. What rotation is this? This is a left rotation. So, you do that, and then after that you do a right rotation. So, after search of 12, the splay idea is get 12. Remember here we do not bother about whether whatever rotation you do, my idea is to move 12 to the root. So, what do we do for that? Here we do a left rotation of 12 about 6 and then right rotation of 12 about 15. When we do that, what happens? This happens. So, after splaying with 12, 12 has moved up to the root. Now, our idea here is to move 12 up to the root. So, you have searched for 12, that is why we have put it as blue. After we have searched for 12, we are doing 2 operations, and that operation is called, as a general, is called splay, because what our idea here is to move 12 to the root. So, whatever rotations you need to move 12 to the root, you can do. Here what did we do? We did first a left rotation of 12 about 6, then we did a right rotation of 12 about 15, such that 12 became the root. So, we had splayed with 12, so that 12 became the root. So, this is the idea, And what happens, nodes that are less frequently accessed, like for example 15, which was at the root then, has now moved down the tree, okay, relatively. So, 12 next time, now the idea here is that next time also 12 is likely to be inserted or searched or accessed. So, 12 has now moved up the tree, and what happens, because it is the root, it will take of the order of 1, not even log n. So, that is the motivating example of why we are doing this Splay tree, or why the Splay tree was designed. So, let us talk about some terminology. The Splay tree here uses terminology that is slightly different from the normal usage that we have seen up to this point in binary balanced binary search trees. This is also a balanced binary search tree. So, let x be a non-root node and which has at least one ancestor, then let p be its parent node. These are normal terminologies. Let g be the grandparent node if it exists, and you consider a path from g to x, that is grandparent to x. Okay. Each time we go left, we say that we have done a zig, okay, and each time we go right, we say that we have done a zag. So, this is the terminology that is used. So, what we have? We have x, we have it. Remember, what our aim is to move x to the root as far as possible. Okay. So, what happens? You have a x, and that x has a parent p and has a grandparent. X may have been on the left or the right. So, every time we do a left rotation, we call it as zig rotation, zig, and every time do a right, we call it as zag. So, let us see the. So, there are 6 possible cases that you can have. So, what are the 6 possible cases? The first is a zig. So, what you are doing is you are moving x about its parent. So, this is called a zig operation. Then here is a zig operation. So, you are doing one left, moving x to the parent, and then you are moving that x and replacing the grandparent. So, you have a zig. Both are, you are doing a time we are going left, okay, but actually we are going left is a right rotation. So, that we will not say. In the zig operation, moving left is called x going more towards the left is called a zig operation. So, each time we go right, we say it is a zag operation. So, here we see the first example as zig operation going about its parent. The next is a zig operation. So, you do a zig operation followed by another zig operation. Then we have a zigzag. So, here what we have done is we go right, that is x moves right, and then through a left rotation, and then you do a zig, go right left. So, we have here a zigzag case, then here you have a zag zig case. So, first you do a go right, okay, and then you go right and then go a left. So, that is called a zag zig. Then you have a zag zag, both going to the right, and then you have just a zag. So, these are the 6 operations: zig, 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 zigzag, zag, zig, zag, zag, and zag. So, these are the 6 operations. It is only rotations, but in these terminologies we go left, you call it zig, we go right, we call it zag. To go left, you need to do a right rotation, to go right, you need to do a left rotation. This terminology we have seen also when we are talking about ABL trees as well as red black trees. So, this is these 6 possible cases that you can have. Now, you traverse a tree from the node x and rotate along the way until x becomes a root. So, here we do not look at any balance or any heights or anything. Your main aim is to keep on doing some sort of rotations and such that x finally reaches the root. That is all our aim is. Okay. So, each rotation, if x is root, do nothing. If x has no grandparent, you just rotate x about its parent. If x has a grandparent, then if x and the parent are both left children or both right children, you can have both cases, rotate the parent about the grandparent, okay. Then rotate x about the parent. So, if x and parent are opposite type of children, one left and the other right, then you rotate x about its parent and then rotate x about the new parent, that is the former grandparent. So, I will just repeat this again just to make sure. This is the basic operations of how to make x reach the root, that is all. So, if x is the root, you do not have to do anything. If x has no grandparent, then you cannot do anything. That means it is in only one level. So, x, just rotate x about its parent, whichever rotation is necessary. Now, if x has a grandparent, we are talking about 2 level rotations here. So, if x and its grandparent are both left children or both right children, that is you have a zigzag or a zag-zag operation, then rotate the parent and the grandparent first and then rotate x about its parent. If x and its parent are opposite type children, one is the left and one is right, that is parent is the left of the grandchild and x is the left, parent is right, x is left, or parent is left, x is right, that type. Rotate x about its parent first, look at the order, here we first rotate x and then you rotate x about the new parent. So, this is the operations that we are going to look. So, let us look at the operation. So, insert if you do. Now, there we just talked about the rotation. What is the issue of rotation? We wanted to move x to the root of the tree, that is all we wanted to do. Now, insert, first insert as in a normally binary search tree, which we already saw in that we did it for ordinary binary search tree, AVL tree, red black tree. Similarly, for Splay trees also you do a first insert. Now, once you have inserted the node, then you have to splay. The meaning of splay is make that inserted node now become the root of the tree. If there is a duplicate, the node that holds a duplicate element is splayed if there is one. Next one, find. So, search for the node. If it is found, then you splay the node. Again here what is the meaning of splay? You splay till you reach the root. Now, it is very interesting here. If you do not find the node, because when you are doing a find operation you may land up not finding the node, then on the way to finding the node you would have reached a node, right, in a search operation in a binary search tree you would have reached a node on the path, that last node you splay. Okay. So, here we have 4 types of splay. One is if there is no duplicate during an insertion operation, splay the inserted node. If there is a duplicate, you splay the duplicate node, because that is that is the way it has been defined. Then find, you could either find the node, then you splay that node. If you could not find the node, the last node that you reached, where when you discover there is this node is not there, that node is splayed. The idea is that next time you will search in that area itself. Locality principle is followed in both these cases. So, during insert and find, which node to splay is decided by that philosophy of principle of locality. Now, let us look at the Splay tree operations. When node x is accessed, apply any one of the 6 rotation operations. Remember, zig, zag, zig, zig, zigzag, then we had zag, zig, zag, zag and zag. So, any of the 6 operations you can apply. Single rotations means x has a p, but no g. So, that is the single rotation, that is either it is a zig or a zag, those are the 2 possibilities. Double rotations, x has both the p. Remember the definition of what is single rotation and double rotation when you do it is different, but the actual rotation is similar to any AVL or red black or whatever it is. So, double rotation is x has both the parent and a grandparent, then you do a double rotation. So, there you have the possibility zig zig, zigzag, that is zig, zag zig, zag zag. So, 4, these are the 6 cases. Okay. So, let us first take the zig operation. Okay. Zig is just a single rotation and this is similar to what we do in an AVL tree. Suppose 6 was the node that was accessed using some search operation, then what you have now, the 6's parent is 15, 15 has no parent, so there is no grandparent. So, when there is no grandparent you do only one rotation, a single rotation, and here what you do, it is on the left. So, you do a right rotate. This we have seen this concept of before also in both AVL and red black. So, similarly only. So, 6 you rotate right such that now 6 becomes the parent. So, zig right, zig means it is always right, that is the definition. So, you have done that and 6 has reached the. So, this is a zig operation, a single rotation, a single right rotation. Okay, single right rotation, zig means right rotation only, and you find that the node you have accessed has reached the root. Okay. Zigzag moves 6 to the root, and next time, now this is the crucial part, the next time you access 6, that is the assumption you are making, that if you have searched for 6, you are likely to search for 6 or do some operation on 6 next. So, it will take of the order of 1 because you find 6 at the root. Okay, that is why we call it a self adaptation. Now, you understand the meaning of self adaptation. That is what we do. We do the balancing in such a way that remember that what has happened is we have not changed any, we have not made it less height things and all that, but what we have done is we have made sure that the 6 has reached the root. This is the right rotation of an ABL tree, normal right rotation of an ABL, which I already told you. Next, let us go to the zig-zig operation. That means you have, it is a double rotation. Okay. So, this is a 2 single rotations of the same type zig. So, here suppose you have 3 was the node that was accessed. Now, so using search operation, we are using search for simplicity here, and now 3's parent is 6 and grandparent is 15, which we see here. And so first what you do, if it is the same, you first do the parent if it is both same operation. Now, this is what is the difference. Remember, we have 4 cases of double rotation, zig zig, zig zig, zag zag, zigzag and zag zig. So, there are 4 operations, 4 types. In this we are now talking about same type. So, zig zig. So, when you talk about zig zig, you first do parent about grandparent. So, that is the first operation you do. So, what happens? 6 is the parent that has moved to up to the root, and now the original node x, which is 3, which was at the second level, has moved to the first level. So, this is the zig right operation. Then now what you have to do? You have to do again a zig operation. So, that is what you do, you single rotate 3 about 6, x about the parent. So, that is what you do. And so, now what you have is a tree which is similarly balanced as the first tree, but 3 has reached the root, and which is the rhyme. So, the 3 which was searched for and which you think will be accessed next, you are going to get that node in of the order of 1 time, because it has reached the root. So, here you have 2 AVL right rotations, single right rotations. So, due zigzag playing, 3 has bubbled to the top, that is our aim. And note here, in this same type of rotation case, first we rotate the parent about the grandparent, and then the node x, or the node that we want to reach the top, about the parent. So, that is how we do this. This is the zig-zig operation. Now, we will go to the third type, which is the zag-zig operation. In the zag-zig operation, as we have seen, it is 2 different types of rotations, a double case only. So, zigzag consists of, zigzag operation has 2 rotations of the opposite type. Now, suppose you have 12, so we are talking about the zigzag operation. So, suppose 12 was the node that was accessed using search. So, what you do here is, first you do a zag operation of, now you look here, you have the parent coming at the left and the child coming at the right. So, the first thing you do is you do a zag left operation. So, what you do here is a zag left operation, single left rotate of x about the parent. So, you do that, and then you do a so what you get is this, and next you have to do a right rotate, as you have understood, zig right. So, you take the right rotate and x about its original the grandparent. So, now what happens? 12 gets rotated, and so you have it is very good, well balanced. So, now 12 has reached the root. So, what you do first is a zag operation, and then you do a zig operation. So, this is called the zag-zig operation, not the zigzag operation, it is called the zag-zig operation. So, what you first do is you do a zag. When you have a zag, it is a left rotation. When you do a zig, it is a right rotation. So, you do a right rotation. So, this is the zag-zig operations. Due to zag-zigs playing, 12 has bubbled up the top. Notice that this is simply LR imbalance correction in AVL tree terminology, first a left and then a right. So, it is the same thing that we talked about here, terminology is slightly different, and the aim here is to bring 12 up to the root. Okay. Now, you have the zigzag operation. The zigzag operation consists of 2 rotations of the opposite type. So, here we have the example. So, first you do a right rotation. So, please note here 17 is x, 20 is p, and the grandparent is 15, and what has happened is 17 is to the left of the parent, but the parent is to the right of the grandparent. So, the first thing you do is a right rotate. So, that is a zig. So, zig right, and then you do a zag which is the left rotation. So, sag left, and now what we wanted was 17, which has reached the bubble to the top of the tree. So, this is a zigzag operation. Due to zigzag splaying, 17 has bubbled to the top, fine, and notice that this is simply an RL imbalance condition where we did first a right and then a left, like we did in an AVL tree. Now, if you look at both these cases of opposite, that is zag zig and zigzag, in zag we did a left first and a right next, in a zigzag we did a right first and a left next. In both these cases we first did the rotations in this way, and in both these cases what happened is the tree has become more balanced on a whole. So, these are the two double rotation cases we have seen. Now, we go to the zag-zag case. In the zag-zag case, two single rotations of the same type. So, suppose 30 was the node that we wanted to do. Now, here there is a slight difference in how we go about this. What we do is, we do the parent rotation about the grandparent first and then do the child rotation about the parent. So, that is the difference here. So, you can see this. So, first do a zag left, okay. Any left rotation, right left rotation is a zag operation, and then you do again a. So, now what happens, you have done 20 and 15 you have done a rotation. Now, 20 becomes the parent and the parent, now you do the x about p. So, again a zag left, and so now 30 has bubbled to the top, which is what we want. So, you will note here there is a slight difference in how we go about this. The original parent has now become the the parent of the original grandparent, because we have completely changed the way in which the tree has been organized. So, here again as you notice 30 has bubbled to the top. Note here that the parent grandparent rotation is done first. In the previous two opposite types, that is zigzag and zag zig, first we did the node about the parent, then the parent about the grandparent. Here we do the parent grandparent rotation first, then we do the child parent rotation. So, the next obvious case is the sag operation. So, sag again is a single operation, again as in an AVL tree. Suppose 15 was the node that was accessed as before. This is a simple case after what all we have seen, we just rotate it. So, you have a zag left, and this is what happens. So, again zag left moves 15 up to the root, and you can access 15 of the order of 1. In all the 6 cases we were moved it to the root, and it could rotate it, find it in the order of 1. So, notice that this is most of the cases the rotations are simply left rotation and right rotation as we defined it in AVL tree. Only thing is, what are the nodes we are doing the rotation with is what is changing. If you would have noticed in AVL, in red we did, in red black we did little more manipulations because of color change and all that. But basically the rotations that we did either in AVL or in red black or in splay, everything the rotations you go either to the rotate to the left or rotate to the right. So, this is the basic operation. So, the operations of rotations and left rotation, right rotation does not change for any of balanced search tree operations. Now, let us take a simple example and see what happens. If you see here we have 40, this is a series of operations. Remember, we wanted to make sure that 40 which was accessed reaches the top of this tree. Now, in all the cases we saw before, we just had 3 levels, right, one level up and the next level up, grandparent. Now, we will see how a series operates. So, first we do a zig operation, and when we do a zig operation, what happens after the zig operations, so after the zig operation 40 changes direction. So, and then you have the 40 moving up, okay, and then you do a zig operation, then you do again a zig operation. This is a series of zig operation because everything is to the left. So, 40 moves up, then it moves up again, then it moves up again, then it moves up again till it reaches the root. So, this is a typical series of operation that you will do. This is called splaying about 40. In this it was an easy case because everything was zig, it was all in this direction, everything was zig. So, 40 from level this level at the after 4 zig operation it has reached the root, which is what we wanted. So, next time you access 40 you will get off the order of 1. Okay. So, then let us assume that 60 is up, this is a different type. So, after 60 is accessed, you have to move 60 up. So, 60 is moved up, and the color codes are telling you about the parent grandparent issue. So, you have the after zag operation, it becomes 60, the second case. Then after that operation, again you do a zig operation, and then you do a zag operation. So, what operations you do depends on where that 60 is. So, you do a zag operation, you do a zig operation, then you do a zag operation. So, after you do the series of zag, zig and zag operations, you have 60 moved to the top, which is your aim. So, next time you do, you access 60, 60 will be of the order of 1. So, that is the idea. Okay. So, why does splaying help? That is the next question, why splaying helps. So, node n and its children are always helped. So, n, not only n's children also move up the node. So, it is all raised means move up the tree, except for the last step. Nodes that are hurt by a zigzag or zigzag operation, zigzag, are later helped by a rotation higher up the tree. So, it is not that I mean they do move lower some nodes, but then later on they will be moved up. So, result is shallow nodes may increase depth by 1 or 2, but help node decrease depth by a large extent. So, what we are trying to tell here, what we are arguing here is that some of the nodes pay a price because you are moving this node which has been accessed the last up the tree, but the amount by which these nodes increase depth, lose the thing, is less than the large amount of advantage you get by moving this node quite a lot up the tree. If a node n on the access path is at depth d before the splay, it is about at depth d by 2 after the splay. So, it is approximately that type of depth decrease. Exceptions are the root, the child of the root and the node are split. If that is true, then there will not be too much of a difference because it is already at the top. During other operations, what do you do? Splaying can be done not just after search, it can be done after operations such as insertion and deletion also. So, insert means after inserting x as a leaf node, as in a regular insertion, you splay that x up the root. Deletion, due to search on x and get x up the root, delete x at the root and move the largest item in the subtree, that is the predecessor up the root or the successor. This is a normal deletion. So, you splay it in such a way. And anyway, the next row, you see when we are doing deletion, if you have deleted x, then you do not have to access x. So, the node that replaces x, either the predecessor or the successor, whichever you feel like, I mean depends on the application, that moves up the root. In search x, if x was not found, then what are we doing? We are moving the node or the last node in the path where you search for that up to the root. So, where you are splaying, which node are you splaying is a question that splay normally does. So, insert, you could do an ordinary search, but that would not fix up the tree. So, you have to do a splay. Better idea, do the splay before the insert, you could have done that also. So, how do we do that? So, split, this is a new operation. So, you split the tree into 2 BSTs, left and right, and all elements to the in the T are either in the left or the right. All elements to the left are less than x obviously, to the right are greater than x. So, L and R, they do not share elements, that is the property. So, then how do we do the insert? Insert as root with children L and R. Okay. So, what you do, split, how can we split? We have the splay operation. We can find x or the parent of where x would be if we were to insert it as in an ordinary BST, and we can splay x or the parent, either one of them, to the root, and then break one of the links from the root to the child. So, this is what we do. Yeah. So, if you have split x, so you do this operation left and right, could be x or what would have been the parent of x, or you could have root is greater than x, so you do an operation like this, and if root is less than x, you put it, attach it in this way. So, this way you have a split operation. So, the insert example, let us assume that we are inserting the node 5. So, what you do, you split S as 4 this way, and then you try to attach 5 as a root to join subtrees using x as the joining factor. So, this is what we get. So, the delete example, you delete, you find 4, delete 4, splay, and then splay on the maximum element in L, and then do the attachment. So, this is what we do. So, what we are trying to do is we are doing, see, in a binary search tree you can do any node can be inserted. So, what we are trying to do is you are trying to rearrange the tree such that this node becomes the root of the either during insertion or deletion. So, what is the analysis? Suggests that splaying causes the tree to get balanced in a way, but balancing was not our idea. So, any sequence of m operation on a splay of size n will take 0 to the m log n time. So, the amortized running time is approximately of the order of log n during a series of operations, and this guarantees that even if the depths of some nodes gets very large, you cannot get a long sequence of the order of n searches, because the splay operation ensures that sometimes you get of the order of n, I mean if you are searching for the same node. Okay. So, without splaying total time would have been of the order of mn. So, what are the advantage? They are arguably the most practical kind of self balancing trees. It is called a self adapting trees, because depending upon the access, that philosophy is there. They are assuming that if you access the node x, the next time also you will be accessing that, does not need any extra information to be stored, and it is balanced in the amortized sense, not every time an operation occurs, and can be adapted to way in which items are being accessed in a dictionary to achieve faster running time for frequently accessed items, which will be of the order of n. So, if the number of finds is much larger then locality is very crucial. So, this is very important, is much larger than n. So, example word counting also supports efficient split and join operation, useful for some other task also. We did not go into too much detail about split and join, but here it is just to say that insertion deletion, if you want you could have done a split and join. That is, if you wanted to do the splaying before you did the insertion, I mean did the operation, and especially important for range queries. So, the summary here is we explain the idea behind splay trees. We discussed 6 cases of the splay trees, 6 cases: zig operation, zag operation, zig zig, zigzag, zag zig and zigzag, zigzag. Describe the operations insertion, find, deletion, and we outline some of the advantages of splay trees. So, we will continue in the next on other types of balanced trees. Thank you.